Namaskar. So, in last class we discussed about the state transition matrix and the state transition equations. So, today we will discuss about the application of state variable analysis in the circuit analysis. So, let us start our discussion of today's lecture. Before going into the application of state variable in circuit analysis, first let us understand what is the relationship between state equations and the transfer functions. So, we know that the linear time invariant system can be described by following the dynamic equation. So, first one is state equation, which we have seen in previous lectures. So, we can say that dx by dt is nothing but ax plus bu. Y is the output equation, y t is equal to cx plus du, where x is considered to be a state vector having n into 1 dimension, ut is input vector having p into 1 as dimension, and yt is the output vector having q into 1 as the dimension. Now, A, B, C, D are the coefficient matrices which correlates the change in the states with respect to its previous state, and similarly C and D define the relationship of state with the output variables. Now, if you take the Laplace transform on both sides of the state equation and rearrange the equation in such a way that you get excess, that is the Laplace transform of the state vector on the left side, then you get S I minus A inverse x at time t is equal to 0 plus S I minus A inverse B u s as the equation. Similarly, if you take Laplace transform of the output equation, you get y s is equal to c into x s plus d u s. Now, in the output equation, if you replace x s with the value which we have just computed for x s, we can write y s is nothing but c into S I minus A inverse into x at time t is equal to 0 plus c into S I minus A inverse B u s plus the component which is there in output equation related to input variable, that is d u s. Now, if you see this particular equation, in this you have the value of x at time t is equal to 0. So, by definition the transfer function requires that initial condition to be set to 0. So, this is what we have discussed when we discussed the transfer function in the previous lectures. Now, if you set initial condition to 0 and simplify the above equation, you get y s is nothing but c into S I minus A inverse B plus d into u s. And what is y s by u s? Y s by u s is nothing but the ratio between output and input, which is nothing but the transfer function of the system. So, the transfer function now you get as c into S I minus A inverse B plus d. So, this is the equation which defines the relationship between state equation and the transfer function. So, if you are given the state equations where you can find out the A, B, C, D coefficients or the coefficient matrices, you can simply calculate the transfer function of the system. Let us take one example so that you can understand what we have discussed. Consider a multivariable system which is described with the help of these two differential equations. So, first is d2y1 by dt2 plus 4 dy1 by dt minus 3y2 is equal to u1. Second is dy1 by dt plus ty2 by dt plus y1 plus 2y2 is equal to u2. Now, let us define the state variables in the system as x1 is equal to y1, so that is one state variable, x2 is dy1 by dt, and x3 is y2. So, when we define these three state variables for the system, we can write these two differential equations in the form of the state variable. So, what you will write for this? So, this is the highest order the component of the differential equation. So, what we will write? We will write d2y1 by dt2 equal to minus 4 dy1 by dt plus 3 y2 plus u1. Now, if you put the value of the state variable which we have just assigned, so d2y1 by dt2 can be written as dx2 by dt, or you can simply write x2 dot equal to minus 4 dy1 by dt is nothing but x2 plus 3 y2, y2 we have defined as x3 plus u1. So, you have got the first differential equation converted into state equation. Similarly, for the second one, let us take dy2 by dt on the left. So, what you can write, since y2 is x3, you can write x3 dot equal to minus dy1 by dt means minus of x2 minus y1, that means minus of x1 minus of 2, what is y2? y2 is x3 plus u2. Now, you have these two differential equations converted into state equations. When you rearrange, you will get what? The differential equations can be converted into the state equation. So, 2 we have got x2 dot, we have got x3 dot, but we need to get x1 dot also. So, x1 dot from where you get? So, if you see this equation, this is nothing but x1 dot equal to x2. So, now you have three state equations. If you compile it into the matrix form, what you can write? So, that is x1 dot, x2 dot and x3 dot equal to, if you take the coefficients using these three equations. So, for x1 dot you can write 0 1 0 because only x2 is the component. For x2 dot you can write minus 4 x2 plus 3 x3. So, you will get minus 4 and 3 as an output. Similarly, for x3 you will get minus x1 minus x2 minus 2 x3. So, this will become minus 1 minus 2 as the coefficients of the matrix, and x1 x2 x3 is the state vector. Now, the input, so we do not have any component related to input in this equation. So, we will use 0 for this, and for x2 dot and x3 dot we have u1 and u2. So, if you arrange it in the matrix form, you can write for u1 u2, first equation does not have any input, for second we have u1. So, you have 1 0, and for second one we have u2. So, you will have 0 and 1. So, this is what you get from the differential equation. So, now you have got the state equation. Similarly, the output equation, if you see, the output is y1 and y2. So, these are the two variables which we only have in the differential equation. So, we take y1 and y2 as an output. So, y1 and y2 is the output. Now, y1 y2 has to be represented in the form of the state variable, that is x1 x2 x3. So, y1 is nothing but x1 and y2 is nothing but x3. So, this we have defined in our initial assumption. So, we take this y1 and y2 as an output variable and compile the state equation. So, we get the output equation as y1 y2, and in the matrix we get 1 0 0 and 0 0 1 x1 x2 x3. Now, since we do not have any input variable in the output equation, the D coefficient matrix will be 0. So, now this you will get as A, this you will get as B, and this is what you have as C matrices. D is of course 0. So, now if we have to find out the transfer function of the system, we will use the derivative which derivation which we have got for the transfer function, that is H s is equal to C S I minus A inverse B plus D. Since D is 0, so H s will become C into S I minus A inverse into B. So, now you have transfer function H s is nothing but C into S I minus A inverse B. Now, first we need to find out the value of S I minus A. So, we compile S I minus A and take the inverse. So, when you take the inverse, you need to find the determinant. So, this will be the denominator for the inverse. So, the inverse you will get 1 upon determinant of S I minus A matrix multiplied by the inverse the matrix. Now, you have got the inverse of S I minus A. Now, if you multiply with the C and B matrices in this fashion, you get the transfer function as shown in the slide. So, here you will see, since we have the two variable, means we are talking about multivariable systems, that is why we are not getting one single transfer function, but the matrix of the transfer functions. Now, let us start our discussion related to state variable method to our circuit analysis. How we will carry out the circuit analysis with the help of state variable methods. So, we will discuss. Now, since many engineering system we see have multiple input and multiple outputs. So, that is why the state variable method is very important tool in analyzing and understanding such complex systems which have multiple input and multiple outputs. So, therefore, the state variable model which we have just discussed is more general than the single input single output model which we generally see in case of the transfer function. So, what we do in state variable model, we specify a collection of variables that describe the internal behavior of the system, and these variables are known as state variables of the system. These are the variables that determine the future behavior of the system when present state of the system and the input signals are known to us. So, that means the state variable which you find will give you the future behavior of the system. With respect to our electrical circuit, the state variables we generally consider as inductor current and capacitor voltages, because they collectively describe the energy state of the system. Now, let us see how we will implement it. So, to apply the state variable analysis to our circuit analysis method, we follow the following three steps. First step is that we will select the inductor current I and capacitor voltage V as a state variable. We have to make sure that they are consistent with the passive sign convention which we discussed in our initial lectures. Now, let us apply KCL and KVL to the circuit and obtain the circuit variables. So, the circuit variables are voltages and currents in terms of these state variables. This should lead to a set of first order differential equation, because when you talk about the voltage and current, voltage across capacitor and current through inductor, you will get the differential equations which is necessary and sufficient to determine the state variables. Now, obtain the output equation and put the final result in state space representation format. So, to see how we can implement this, we will take couple of examples so that you can understand this concept very clearly. let us take one example. Here we have a state space, we need to find the state space representations of the circuit, which is shown in the figure below. We need to determine the transfer function of the circuit also. Here Vs is the input and Ix is the output. So, we need to find the value of Ix and Vs is given as an input. The value of resistance R is 1 ohm, capacitance is 0.25 farad, inductance is 0.5 Henry. Now, in this particular circuit, what we will do? We will first select inductor current I and capacitor voltage V as the state variables. So, when we see them as a state variable, what we can first find? We can find VL, that is voltage across inductor, is nothing but L into di by dt. The capacitor current, that is IC, you can write as C dV by dt. So, these are the equations which we have already discussed in our previous lectures. Now, let us apply the KCL at node 1. So, when you apply KCL at node 1, what you can write? You can write I is equal to Ix plus Ic. What is Ix? If you see, Ix is nothing but the voltage across capacitor, which will be also applied across the resistor. So, Ix will be nothing but V by R. So, we have taken Ix as V by R and current I, which is unknown. So, what we are doing? We are rearranging this equation. We are taking Ic, that is C dV by dt on the left. So, what we get on the right is I minus Ix, which is minus V by R. If you divide by C, you will get dV by dt is equal to I by C minus V by C R. What is dV by dt? dV by dt is nothing but V dot. So, this is the first equation we have got while applying the KCL at node 1. Now, next we apply the KVL around the outer loop. We get Vs is equal to VL plus V. So, when you put the value of VL, you get Vs is equal to L into di by dt plus V. If you put L di by dt on the left and rearrange and then divide the right side with L, you get di by dt is nothing but minus V by L plus Vs by L. Now, when you get this, di by dt is nothing but I dot. So, you got the second equation for your state equation representation. Now, from the equation 1 and 2, we get the state equation. Now, if we take Ix as an output, then Ix will be represented as Ix, we have just saw Ix is nothing but V by R. So, if you compile these equations, that is 1 and 2 in the standard form, we get the following state equation. So, on the left we have V dot and I dot equal to minus 1 by R C, 1 by C as the elements of the matrix, minus 1 by L and 0, which corresponds to I dot, and when you arrange, you get the state equation. Similarly, Ix is equal to V by R. So, using this you get the output equation. Now, you have got A, you have got B and you have got C. Of course, D is 0. So, what we will do? We have A is equal to minus 1 by R C, 1 by C, minus 1 by L and 0. So, these are the matrix element. If you put the value of R and C, you get A as minus 4, 4, minus 2 and 0. So, these will be the elements of matrix A. Similarly, for vector B, these are the elements 0 and 1 by L. So, you get B as 0, 2. Similarly, C, you get the elements as 1 by R and 0. If you put the value of R, you will get C as 1, 0. So, now you have got A, B and C. The next task is that we find first the value of Si minus A matrix, then we invert it. So, we get this matrix. Then finally, we need to find the transfer function of the circuit. So, we get C S I minus A inverse B. If you put the value of all these matrices and simplify, you get the transfer function H s as 8 upon S square plus 4 s plus 8. So, now you can simply say that the transfer function related to the electrical circuit which we have in the example is given by H s equal to 8 upon S square plus 4 s plus 8. Now, let us take another example. So, consider the circuit which is shown in the figure below, which may be regarded as a 2 input and 2 output system. In the previous case, we saw the simple single output system. Here we have 2 input and 2 output system. In this case, we need to determine the state variable model and the transfer function of the system. Now, what we will do in this case, we have 2 inputs. What are those inputs? V s and V I are the 2 inputs in the circuit, and we have 2 outputs. So, we need to find the value of V naught and I naught. V naught is the voltage across 2 ohm resistance and I naught is the current flowing through the 3 ohm resistance. So, V I and V s are considered as an input in this case, and V naught I naught are the outputs. So, as we did in the previous case, in this case also we select inductor current and capacitor voltage as the state variables. So, first what we will do? We will apply KVL around the left hand loop. So, this is the left hand loop. If you apply KVL, what you can write? Minus V s plus I 1 into 1 ohm equal to minus I 1, then plus 1 by 6 into d I by dt, because voltage across this is L d I by dt, L is 1 by 6. So, you get plus 1 by 6 d I by dt equal to 0. Now, if you rearrange, you can write d I by dt, that is nothing but I dot equal to V s minus I 1 into the value of 6 which you have. Now, we need to eliminate I 1 from this and apply KVL around the loop containing 1 ohm resistor, 2 ohm resistor and 1 by 3 F farad capacitor. So, if you apply KVL around this, what you get? V s is equal to I 1 plus V naught plus V. So, this is the loop which we are considering for applying the KVL. So, V s you get I 1 plus V naught plus V. So, what is I 1? I 1 you can get from KCL while you apply this KCL at node 1. So, I 1 is nothing but I plus the current flowing through 2 ohm resistance, that is V naught by 2. So, you get V naught is equal to 2 into I 1 minus I. Now, from the above two equations, what you can write? You just put the value of V naught in this. So, we will get V s is equal to 3 I 1 plus V minus 2 I, or simply you get I 1 as 2 I minus V plus V s by 3. So, you get now I 1 in terms of the other components. So, we can in this way we can eliminate the I 1 from the equation. Now, putting the value of I 1 in this equation, that is I dot is equal to V s into V s minus I 1 into 6. So, this is V s minus I 1 into 6. So, when you simplify d I by dt is nothing but I dot equal to 2 V plus 4 I minus 4 I plus 4 V s. So, this you get with the help of this. So, when you put this value here and simplify, you get 2 V minus 4 I plus 4 V s. So, now you got one equation. Now, to obtain the second one, what we do? We apply KCL at node 2. So, if you apply KCL at node 2, what you get the current flowing through 2 ohm resistance is V naught by 2, that will be equal to current flowing through the capacitor. So, you can write 1 by 3 into dV by dt. So, you have got 1 by 3 dV by dt you can represent as V dot plus the current which is flowing in this is equal to I naught. So, when you simplify V dot you can write equal to 3 by 2 V naught minus 3 I naught. Here again we have to eliminate V naught and I naught, because this is the state equation and V naught and I naught are the outputs. So, we need to replace V naught and I naught in the equation which we have V dot equal to 3 by 2 V naught minus 3 I naught. Now, to eliminate, what we will do? We get from the right hand loop I naught is nothing but, we know that this is the voltage across capacitor is V. So, what we can write? V minus V I by 3 is equal to I naught. So, this is we get from this loop, and from the previous discussion, that is V naught we have got as 2 into I 1 minus I, and I 1 we have got as 2 I minus V plus V s by 3. So, if you put the value of I 1 in this equation and simplify, we get V naught is equal to minus 2 by 3 into V plus I minus V s. Now, we have got the value of I naught and V naught, we put these values in this above equation and simplify. When we simplify, we get dV by dt, that is V dot is equal to minus 2 V minus I plus V s plus V I. So, now you have got the second state equation, this was the first one. So, now if you compile it in the form of the matrix, the state equation which you can now write as V dot I dot, these are the state vector, equal to minus 2, minus 1, 2 and minus 4 are the elements of the matrix A. Then V I is the state vector, plus 1 1 4 0 will be the value of B, that is the input vector V s and I s, because here we have two inputs, that is V s and V I. So, that is why you get 4 elements in the B matrix, and then output equation you can compile, because V naught and I naught we have just found, that is I naught is V minus V I by 3 and V naught is equal to minus 2 by 3 V plus I minus V s. So, using these two equations you can compile it, that is V naught I naught, that is the output vector, equal to the C matrix into the state vector, that is V I, plus the D matrix multiplied by the input vector, that is V s and V I. So, with this you can now understand that how you can convert this particular the circuit into a state space representation. Now, you have A, B, C and D. So, the transfer function you can simply calculate, that is S I minus A inverse B plus D. So, put the values of A, B, C, D in this matrix and simplify, you get the transfer function H S. So, with this we can close our today's discussion. In this session we discussed mainly about the application of state space state variable equations in the circuit analysis. We will continue our discussion related to other aspects of state variable in our next lecture. Thank you.